NFPA 70-2005, Article 450 Transformers and Transformer Volts 450.2 Transformers installed indoors, be over 600 volts nominal, 1 grounding. C. The grounding conductor shall not be smaller than the size required for the grounded conductor of the circuit to which the transformer is connected. D. For Wye-Wye connected transformers, the grounding conductor shall be connected to the grounded neutral conductor on the secondary side of the transformer. The National Electrical Code, or NEC, provides specific guidelines for the installation and grounding of transformers, particularly Wye-Wye connected transformers. These guidelines are essential to ensure safety, prevent electrical hazards, and maintain the integrity of the electrical system. Article 450 of the NEC specifically addresses transformers and transformer volts, and within this article, Section 450.2 focuses on transformers installed indoors. When dealing with transformers operating at over 600 volts nominal, there are stringent grounding requirements outlined in subsection B. These requirements are put in place to protect personnel and equipment from potential hazards associated with high voltage systems. One key aspect of these grounding requirements, as stated in paragraph C, is the sizing of the grounding conductor. The NEC mandates that the grounding conductor must not be smaller than the size required for the grounded conductor of the circuit to which the transformer is connected. This requirement ensures that the grounding conductor has sufficient capacity to safely carry fault currents back to the source, thereby minimizing the risk of electrical shock or fire. Moreover, Paragraph D of Section 450.2 provides specific guidance for Wye-Wye connected transformers. It stipulates that the grounding conductor must be connected to the grounded neutral conductor on the secondary side of the transformer. This connection is crucial for establishing a low impedance path for fault currents and preventing the grounding conductor from carrying load current under normal operating conditions. In a Wye-Wye transformer configuration, the primary and secondary windings are both connected in a Y configuration. The neutral point of each winding is typically grounded to provide a reference point for voltage and to facilitate the flow of fault currents. When the grounding conductor is connected to the grounded neutral conductor on the secondary side, it creates a direct path for fault currents to return to the source. This path helps to quickly trip over current protection devices such as circuit breakers or fuses, thereby isolating the faulted circuit and preventing further damage or hazards. Without a proper connection to the grounded neutral conductor, the grounding conductor may become a path for load current, which can lead to several problems. Firstly, it can cause the grounding conductor to overheat, potentially leading to insulation damage and fire hazards. Secondly, it can create voltage drops along the grounding conductor, which can affect the performance of sensitive electronic equipment. Thirdly, it can increase the risk of electrical shock, as the grounding conductor may not be at true ground potential. Therefore, adhering to the NEC requirements for grounding Wye-Wye transformers is essential for ensuring the safety and reliability of the electrical system. By properly sizing the grounding conductor and connecting it to the grounded neutral conductor on the secondary side, electrical professionals can minimize the risk of electrical hazards and maintain the integrity of the system. Now let's delve a bit deeper into why this specific grounding configuration is so important, particularly for Wye-Wye transformers. To fully understand the necessity of connecting the grounding conductor to the grounded neutral on the secondary side of a Wye-Wye transformer, we need to explore the behavior of currents in a three-phase system and the role of the neutral point. In a balanced three-phase system, the currents in each of the three phases are equal in magnitude and displaced by 120 degrees in phase angle. Under ideal conditions, the sum of these three currents at any given instant is zero, meaning there is no current flowing in the neutral conductor. However, in real-world scenarios, electrical systems are rarely perfectly balanced. Loads on each phase may vary, leading to unbalanced currents. This imbalance causes current to flow in the neutral conductor, as it provides a return path for the difference between the phase currents. In a Y-connected system, the neutral point is the common point where the three-phase windings are connected. If the neutral point is not grounded, it can float to a voltage potential that is different from ground. This can create several problems. Firstly, it can cause voltage imbalances between the phases, leading to erratic behavior of equipment connected to the system. Secondly, it can increase the risk of overvoltages, particularly during transient events such as lightning strikes or switching operations. Thirdly, it can make it difficult to detect ground faults, as there is no established reference point for ground potential. By grounding the neutral point, we provide a stable reference point for voltage and ensure that the neutral conductor remains at or near ground potential. This helps to maintain balanced voltages between the phases, reduce the risk of overvoltages, and facilitate the detection of ground faults. Now, let's consider the scenario where the Wye-Wye transformer is connected with the H0 bushing only connected to the grounding conductor, and without a grounded neutral conductor on the secondary side. In this situation, the grounding conductor would be forced to carry any neutral current resulting from unbalanced loads. This is problematic for several reasons. Firstly, the grounding conductor is typically sized to carry only fault currents, not continuous load currents. If it is forced to carry neutral current, it may overheat and potentially fail, leading to a loss of grounding. Secondly, the grounding conductor may not be adequately sized to handle the neutral current, especially in systems with significant load imbalance. This can result in voltage drops along the grounding conductor, which can affect the performance of sensitive electronic equipment. Thirdly, the grounding conductor may not provide a low impedance path for fault currents, which can slow down the response time of overcurrent protection devices and increase the risk of electrical shock. By connecting the grounding conductor to the grounded neutral conductor on the secondary side of the transformer, we provide a dedicated path for neutral current separate from the grounding conductor. This ensures that the grounding conductor is only used for its intended purpose of carrying fault currents, and that the neutral conductor is adequately sized to handle any neutral current resulting from unbalanced loads. In addition to the NEC requirements, there are also practical considerations that support the need for a grounded neutral conductor in Wye-Wye transformer systems. For example, many electronic devices rely on a stable ground reference for proper operation. If the neutral point is not grounded, these devices may experience erratic behavior or even fail to operate correctly. Furthermore, a grounded neutral conductor can help to reduce electromagnetic interference, or EMI, in the electrical system. EMI can disrupt the operation of sensitive electronic equipment and cause communication errors. By providing a low impedance path for ground currents, a grounded neutral conductor can help to minimize EMI and improve the overall performance of the system. It is also important to note that the NEC requirements for grounding Wye-Wye transformers are based on years of experience and research. These requirements have been developed to provide a safe and reliable electrical system that protects people and property from electrical hazards. Ignoring these requirements can have serious consequences, including electrical shock, fire, and equipment damage. Therefore, it is essential for electrical professionals to understand and follow the NEC requirements for grounding Wye-Wye transformers. This includes properly sizing the grounding conductor, connecting it to the grounded neutral conductor on the secondary side, and ensuring that all connections are made in accordance with the code. In summary, the NEC requires that for Wye-Wye connected transformers, the grounding conductor shall be connected to the grounded neutral conductor on the secondary side of the transformer. This requirement is crucial for establishing a low impedance path for fault currents, preventing the grounding conductor from carrying load current, and ensuring the safety and reliability of the electrical system. By adhering to this requirement, electrical professionals can minimize the risk of electrical hazards and maintain the integrity of the system. Remember that while I've been discussing the NEC 2005 edition, it is always crucial to refer to the latest edition of the NEC adopted by your local jurisdiction. Electrical codes are updated periodically to reflect new technologies, best practices, and safety concerns. Ensure you are working with the most current and applicable regulations. Furthermore, always consult with a qualified electrical engineer or inspector for specific applications and interpretations of the code. They can provide valuable guidance and ensure that your installations meet all applicable requirements. Now I will give a summary of what was discussed. Firstly, NEC Article 450.2 Bone. C mandates the grounding conductor size must be no smaller than the required size for the grounded conductor of the circuit connected to the transformer. Secondly, NEC Article 450.2 bone. T specifically addresses Wye-Wye transformers, stating the grounding conductor must connect to the grounded neutral conductor on the secondary side. Thirdly, the purpose of this configuration is to establish a low impedance path for fault currents, enabling quick tripping over current protection devices like circuit breakers or fuses. Fourthly, without a grounded neutral connection, the grounding conductor may carry load current, causing overheating, voltage drops, and increased shock risk. Fifthly, grounding the neutral maintains balanced phase voltages, reduces overvoltage risks, and facilitates ground fault detection. Sixthly, Wye-Wye transformers without a grounded neutral can lead to erratic behavior of connected devices and increased electromagnetic interference. Seventhly, the NEC requirements are based on experience and research aimed at creating safe and reliable electrical systems. Eighthly, ignoring these requirements can have severe consequences, including electrical shock, fire, and equipment damage. Ninthly, electrical professionals must understand and follow the NEC requirements, including proper grounding conductor sizing and connection to the secondary grounded neutral. Tenthly, always consult the latest edition of the NEC adopted by your local jurisdiction and seek guidance from qualified electrical engineers or inspectors. Adhering to these principles ensures a safer and more reliable electrical system.